Welcome to the name training video on name outputs, how we output data from name. So far you've looked at the science behind name and some examples of how we use name in the Met Office. You've also looked at how an input file is configured and how you might change that input file for the type of run you want to do with name. But what's really important is how we output data from name, how we get out the output we need in order to be able to plot the data, carry out further analysis on the data, and carry out statistics on the data. And so in this lecture, we're going to look at how we customize the output from name so that we can request the information we require for the task we're doing. So we're going to look at how we request field output from name, how we specify the spatial and temporal averaging, how the output file is formatted so that we know how we might use it in that further analysis. We're also going to look at another type of output from name, trajectory output. And then finally, I'm going to outline the capabilities of Iris, which is a Python package built at the Met Office, specifically for analysing large data sets such as climate and weather data sets. So first of all, what do we mean by a field output? Well, internally in name, a field is a four-dimensional array. So it consists of the four dimensions x, y, z, and t. It has a h grid, a z grid, or a t grid. Now, for any particular data set, each of these dimensions might be collapsed to a single point. So instead of having a z grid with a range of z values, we may have a single vertical level or a boundary layer average. We can also add a fifth dimension to our data set. We call this a statistical dimension, which isn't a typical dimension, and I'll explain a little bit more why we do this and how we do this in a later slide. Might also help to look visually at what a field looks like. So here are some examples of fields. If you look here on the left-hand side, we can see a classic example of a field. So this field has an x and y dimension, and in this particular snapshot, we can see that both z and t are held constant. But there are many other fields that we might want to request from name. So for example, up here in the top right, we might wish to request a field which is a function of t and z. So in this case, x and y, the horizontal location is kept constant. And of course, we can collapse all bar one of our dimensions. So if we look here at the picture in the bottom, we have data which is a function of time only. So in this image, x, y, and z, the horizontal and vertical grids, are all kept constant. So how do we go about requesting a field from name? So we have a block in name input file, which is called output requirements-fields. Now this is quite a long line because we can be very specific about the output requirements we want to request. So I've put an example here in the grey box, but you'll see that it's truncated on the right hand side. So if you were to pause the video now and look at the input file you've been given for the training course, you'll see that the line is actually much longer. So in this case, we're requesting the air concentration of strontium 90 on a H grid we've called here H grid for fields, a Z grid which appears blank, and a T grid which we've called the main T grid. So the lines are long so that we can be very specific about the output requirements that we want. We can specify horizontal and vertical grids and their averaging. We can specify the temporal frequency and averaging, and we can also make requests about the output format and the layout. And we're going to look at each of those in turn in the next few slides. Horizontal averaging or integrating. So as we saw in the last slide, we specified our horizontal grid as H grids for fields, which obviously doesn't give the computer any information about what we want our H grid. So we now need to look at another block in our input file, and this block is called horizontal grids. And we can specify a horizontal grid, H grid for fields, for example, by specifying its latitude and longitudinal extent. So in this case, if we look at this top example, we can see that we've chosen a regular gridded output. In this case, we've specified that the coordinates would be latitude and longitude, that the grid would start from a longitude minimum of minus 35.59 degrees and a latitude minimum of 17.38 degrees. that the grid will have 300 points in the latitudinal direction and 300 points in the longitudinal direction, and that the longitudinal range will be 59.8 degrees and the latitudinal range will be 44.8 degrees. If you want to specify your gridded output in a different way, you can look into the input file document and you'll see a number of ways in which you can specify a horizontal grid. The other typical horizontal grid that we might want to output is that we might have some observation stations that we wish to output data at. And we can see an example of this in the second line here. So in this case, we've called it hgrid for time series. And in this case, we've only specified a longitudinal and latitudinal extent of our grid box. And then we've asked name to output at what we've called a set of locations. And here this is output locations. And like we had with the hgrid, this is actually another block in name. So you will find another block in name called output locations, a bit like the source locations you learnt about earlier, listing all the latitudinal and longitudinal points of the output locations you wish to output at. So that is the example for outputting a specific hgrid. But as you saw from the zgrid, we can also leave the line blank. So if we were to leave the hgrid blank, then the output is horizontally integrated across the whole domain. So for example, if you wish to learn how much mass is still remaining in the atmosphere, then you would put in a blank space for your hgrid in your output requirements block. So now on to our vertical averaging or integrating. In the vertical grid, we can specify our zgrid as either discrete vertical levels, i.e. a distinct point, or as vertical layers where the quantity is averaged over a number of layers. So for example, a discrete vertical level might be 10 meters. That might coincide with a height of a particular observation, or we might want to average the concentrations between, say, 0 and 100 meters. So what does this look like? Well, we have, like the horizontal grids, we have a block called vertical grids. Each vertical grid has a name, a coordinate, and then some dimension specifications. So our first grid here, zgrid for field, is specified in meters above sea level, MASL. And we can see here that we have 10 levels or under NZ, and that each level is 50 meters high, and that our first level, our Z0, is at 25 meters. So our first level, being 50 meters high with a central point at 25 meters, will stretch from 0 meters to 50 meters. Alternatively, we have here on the second line a discrete vertical level example, and this is a zgrid for MET output. In this case, we've specified in meters above ground level. In this case, we've also only got one level, so NZ equals 1. And you can tell it's a discrete vertical level because DZ is 0. In this case, we've got Z0 equals 10 meters. Now, in a similar method to the method used for hgrid, we can also specify no zgrid. So you saw on the first slide that our output requirements block had no zgrid. Then there are two things that we might do after this. Firstly, we could then have a boundary layer average. So we would put boundary layer average question mark equals yes. And in this case, name will work out the boundary layer height at each time step and average the quantity over that boundary layer. And this is particularly useful if we're interested in quantities which have an impact in the boundary layer or an impact on humans. So where we're interested in the concentration that we're experiencing at the ground once the material has been well mixed vertically. The second option is to leave the zgrid option blank and the boundary layer average option as no. And in this case, the quantity will be vertically integrated over the whole domain. So for example, if you were using a satellite and wanting to compare to satellite data, you might choose to vertically integrate over the whole domain so that your name output looks like the output that you might get from a satellite. Now we move on to our temporal averaging or integrating, and there are a number of options open to us here. So we might want to consider either instantaneous fields or time averaged fields or time integrated fields. And these are all controlled in the column which has the heading T, av or int. So for instantaneous fields, we would put no, averaged fields, av, and integrated fields, int. But it's also possible to control the period over which our integrals and averages are calculated. And because this is a Lagrangian model, we can also calculate the number of contributions which are used in order to calculate that average or integral. Let's move on to the next slide to see how this is done. So you can imagine that you want to request hourly output of your data, and you've decided that you would like an average. So name is a Lagrangian model. It follows with a very small time step, each particle at each time step in time. And what we need to do is we need to specify how often we want to regrid that data onto a grid to compute the averages. So in this case, we've put hash averaging times equal to 6. So that means that in the hour, we're going to take 6 snapshots of the data. So we're going to look at 6 points in time at what the average contributions in each grid cell are. So effectively what we do is we look every 10 seconds, so that we get contributions at 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, and on the hour. And then the average of those quantities is used to calculate our hourly average. So we've taken a brief look at how we specify the output in terms of its grid horizontally and vertically and its time averaging or integrating. But what is also important to look at is how the output's actually going to appear to us. So fields are usually output from name as an ASCII or text file, which usually has either 2 dimensions or 1 dimension, although actually any combination is possible. And it's possible to decide exactly what you want in your separate columns. So you can use your separate columns for additional dimensions or for different quantities such as deposition or air concentration. And then you can also specify which quantities you want to store in the same file, with the caveat that all quantities in a single file must contain the same grids. So the format of the name output file is controlled by 4 headings in the output requirements fields block: across, separate file, output group, and output format. The first of these, across, controls which of your variables are output to different columns within one file. And the variables, as you might expect, x, y, z, and t. And then we have 2 other variables. S is the travel time of the particle, so a little bit like time, but dependent on the release time of the source particle. And then d is your statistical output, which, as I mentioned, we'll cover later. It's also possible to choose which of these variables are output to separate files. So it might be that you want a separate file for every time step or a separate file for every vertical level. So this is the column headed with separate file, and again you can choose the same variables x, y, z, t, s, and d. We then have an output group. Now the output group actually defines the prefix for the file name. So you might call this, my fields 1 or fields grid 2 or my output for experiment 1. And basically this is the start of the field name. So let's say, for example, that we've decided we'll put out Z across and then we'll put T into a separate file. So then our output group will have the prefix that we've defined, say fields grid 1, and then it'll have an underscore, and then it'll have some time information for the fact that each of those files will be a separate time step. This will become a bit clearer when you start to run name. But it's important to remember that output, if you can put on each output requirements line, you can use the same output group name, and those variables will then all be written to the same file. So I think before I mentioned that the separate columns could be different quantities, so it could be air concentration and deposition. In your output requirements block, you'll have separate lines for air concentration and deposition, but they can both have the same output group, and then that will ensure that they both end up in the same output files. And the final thing you need to mention is that you can specify the output format. And there are 3 options here. You can have I, which will include grid point indices. So instead of columns which just have X longitude and Y latitude, you can then have the index of X and the index of Y. This can be particularly useful in some plotting programs. You need to include A to align columns. This is actually now compulsory due to some changes in names, so you can't leave this one out. And then you can include Z to include points with 0 values. So you can see the advantage of this. If we've got a large fields grid and our plume is quite small, then by not including Z, as in not including points with 0 values, we can shrink our file size quite massively. However, it might be that for whatever statistics you're doing, it's important to output those zeros, in which case you would include Z. So this is what a fields file looks like. I apologise for the slightly small size. The best thing to do for this is to pause at this point and to open your own output fields files. But basically what you can see is at the top left, we have a file identifier that just tells us that it's a name output file. So in this case, you can see it says name3 version 6.2. So it provides the version number of the model. The next few lines are all what we call main header lines, and they provide details of the model run. So the time it was run, the output grid, the number of columns you've output in this particular file. We then have a line that breaks the file between the main header and the columns, and this just says fields, and then we have some columns, and you'll see that the first 4 columns are all related to the grid. So here we have an X index and a Y index, which means that in our file formatting we have I. We then have the latitude and longitude corresponding to the X index and the Y index. And then following that on the right, we have columns of data relating to all the quantities we're outputting. And at the top of all of these columns, you'll see some information which describes that output. So we can see that the first column is about a species which is called tracer, and we've called it the 0 to 100 meter average air concentration. It's an air concentration. It's a part of the group of species called the depositing tracer, and it's the data in the column is in the units of grams per meter cubed. And then the header lines below that tell us about the ensemble averaging, the vertical averaging, and the horizontal averaging, as well as the time averaging and the vertical level. This is an example of another fields file. In this case, we've just asked for time series output. So if you remember back to the pictures I gave you, this is our field which is only a function of time. So in this case, the file looks a little simpler, but you can see some common elements with the file on the previous slide. So again, we have a name3 file identifier, and in this case, version 5.2. We then have some header lines which describe the grid and describe the release. Then we have the line that just says fields that breaks the output file so you know where the column headers start. Now in this case we have the X and Y grid were placed in the across column, so there's no columns for X and Y, and there's no index columns for X and Y. In this case we just have a column for T. And then across the top you can see some information about what we've output. In this case some meteorological quantities. Again they're time and horizontal and vertical averaging. And because we've requested that X and Y are across, you can also see that X and Y now appear in the header lines. So finally, I said I would mention some statistical quantities. So NAME is capable of computing statistics online as it runs. So for example, you might want to consider the maximum concentration in the last hour, or you might want to know what the median concentration was in the last hour, or perhaps you want to know the probability of exceeding a certain threshold over the last 6 hours, and that's all possible within NAME. Now this looks a little bit like the time averaging functionality, but is subtly different, so it's just take a bit of care when using it. So here we have an example where we're going to output the maximum percentile, so the maximum concentration over a 1 hour period. So you can see that our time grid is set to 1 hour, and we've asked for a percentile of 100, but actually in this box you could also put a list. So if you wanted the 25th, 50th, 75th and 100th percentiles, you could actually just list those. We've then got the time in which that percentile must have occurred. So we've got a 1 hour period in which we're looking for the 100th percentile. And then we've got a time step that we're looking for that. And so in this case, our time step is 10 seconds. So we're looking for the maximum concentration in 10 seconds in an hour's block. If you want more information on this, you'll find it in the NAME user guide. The second style of NAME output I'd like to tell you about is trajectory output. So, what is a trajectory? Well, NAME is a Lagrangian model, so we follow particles in time, and as well as being able to compute averages by gridding that data and calculating gridded averages, we can actually output the information along each individual particle trajectory, so we can learn about how each particle is travelling. And it's also possible to calculate things like the masses and activity which are carried on each particle, and also to look at the meteorological parameters which kind of describe the meteorological space that each particle is passing through. So we'll look at a visual example. So we've got two visual examples here. In the bottom left-hand corner, you can see one particle plotted over time. So this particle, for example, starts at a point just south of the Grand Banks off the coast of the US. And then it travels northwards, crosses Greenland, loops around Iceland and heads back towards the US. Each of the stars marks every 6 hours in time. So you can see where the particle has travelled over time. But it's also possible to look at many particles at one particular time, as the top right example shows. So these are all the particles that the model is following at 2045, 8:45 on the 13th of May 2017. And what we've plotted here is each particle's position, so you can see its horizontal position in space by where it is on the plot, and then its vertical height is plotted by using the colours, so that you can see that the particles in the blues to the left of the figure are lower in the atmosphere than the particles on the right, which are higher up. And this is a snapshot then of all the particles that NAME is following at one time step. So how do we request trajectory output from NAME? Well, in this case, we use an output requirements block, which is called particle puff information. So output requirements dash particle puff. And we output the data as a function of time. So similar to the time grid that we used before, we can choose a specific time grid, or we can choose every model time step. In this case, we wouldn't specify a horizontal grid or a vertical grid because we're actually asking for the position of the particle at a specific time. So we will just be given that location in both horizontal and vertical space. It is also possible to restrict the output. So you can see in the example below that we've asked for the particle output for the first particle 1 and up to the last particle 4. So we're only asking for output for the first 4 particles, even if we might be modelling millions of particles. This is a good way of outputting just a little bit of particle information as a debugging check for our data. We can also restrict the output, say, to a specific source. So if we're looking at all sorts of different sources of pollution, we might actually only want to output the particle information, say, for the traffic sources as opposed to the industrial sources. And we can also request different things from the particles. So in this case, you can see that we've requested the metadata here, and we've asked for no mass data. So what does the file look like? So this is an example of a trajectory file, and again I apologise for the small size, it wouldn't fit on the page otherwise. So just like the fields file, we have a file identifier at the start which indicates that it's a NAME output file. And you'll also see that, like the fields file, it's an ASCII or text file format, so it's human readable. And it includes the version number. It then includes a little bit of information about the run. So in this case, it tells you the run name, the run time, and some metadata, and it tells you whether the trajectories were running forwards in time or backwards in time. And that's the limit of the main header information. Then we have a gap line, just as before. In this case, the gap line says a set of particle or puff information, and then we have all our data in columns. And you'll see all the different columns here. For example, it tells you the release time of the particle, the travel time of the particle, its location in X, Y, and Z, and if you've requested MET or mass, that information will also be given. So finally, I wanted to mention IRIS. So what is IRIS? So IRIS is an open source Python library developed by the Met Office specifically for analysing and visualising large Earth science datasets, initially weather and climate science datasets, but actually it's now progressed to Earth science datasets. And it handles data as cubes. So if you're familiar with NetCDF files, you'll probably see some of the commonality here between a cube and a NetCDF file. So at the bottom left here, we have an example of a cube, in this case air temperature, and that information is stored on a three-dimensional grid, in this case, X, Y, and height. And you can see also that not only do we have the information about the cube, in the sense that it's air temperature, but we also have metadata associated with the coordinates as well. So we can see that our coordinates are latitude, which is in degrees, longitude, which is in degrees, and height, which in this case is in meters. So the whole object is designed to be self-describing. It describes not only itself and its units, but it also describes its coordinates and their units as well. And we've just got an example on the top right hand side of a name plot that was created using Iris. So if you are able to get hold of Iris, then it's very simple to input name data because all the tools for reading name data are included in Iris. And if you're familiar with Python, you'll recognize some of the formatting here. So the first line would just look import Iris. So it's importing that package Iris. And then we can just do cubes equals iris.load, and we load up our name file. In this case, any file which starts fields underscore grid 2. That's our output group name, if you remember from previous slides. And then we can just print. And in this case, I've just asked it to print the first slide so that you can see how the information in the name file is translated into the cube. So the first thing you'll notice is the cube is given a name, and it's great, isn't it? Name and name. But anyway, name cubes are given a name which is the species underscore the quantity. So in this case, we requested air concentration output of cesium-137. So our cube name becomes cesium-137 underscore air concentration. You can then see a set of coordinates. So clearly this is taken from the coordinate information and name. So this is taken from that header, main header, where the coordinate information is given, as well as the column headers in the case of the height and the time information. And depending on what information is stored in the name file depends on whether Iris is able to put bounds on that. So if we've got, say, time averaging information, say the name file contains the information 3-hour average, then that 3-hour average information can be translated into the bounds of the time unit. The next big set of information is the attributes, and this is all the information that's in the main header file. So things like the start and the end of the release height and location, and all of this information is stored in the attributes of the cube so that you can re-retrieve it. And then finally, the data is stored in cube.data. So the array of data that you've collected in your name file is stored in the cube as well. There are some limitations to name and Iris. So we have two name output formats, name2 format and name3 format. For name2 format, Iris can only read gridded files and time series files. So if you decide, for example, that you want to output a file with T and Z columns, then unfortunately Iris can't deal with those. This is also true of the basic name3 format. So in this case, Iris would expect you to output using I for gridded files. So you will need an X index and a Y index column in your output file. And the time series files can only be output if the horizontal grid is specified using dx, dy, and set of locations, as in the very first example I gave. However, Name also has a newer format called Output Format 2, and in this case Iris can read any file format, regardless of what coordinates are in the columns and which coordinates are in different files. Iris can read them. So over the course of this lecture, we've looked at how we output field and trajectory information at Name, and we've looked at the flexibility of that format and how we specify its horizontal and vertical and temporal grids and how to specify what averaging we want. We've also looked at how we might format that information, how we can choose what information we want in separate columns and what information we want putting in separate files. But we've also only touched the surface of all the possible options for output formats. So I'd fully recommend that you look at the input document and look at the output requirement headers in the input document for more information. If you have any questions, please don't hesitate to contact one of your trainers.